Look at gravitons like energy molecules,
Like particles.
particles.
If you think about like radar, radar sends out pulses and then it bounces off of something.
That's kind of
it's sort of, it sends out something that it doesn't necessarily bounce, it doesn't bounce off them, but I sort of picture it like that. It senses them.
it senses those. Okay.
So if you were in a plane being tracked by radar, if the analogy would be, you know you're being tracked by radar.
Okay.
So that's a justification for the R squared. There are people out there who are trying to figure out, is it really R squared? Maybe it's R to the 2.000001. And what they do is the difference between the actual number and 2 is less than however far they've gotten it down to. It's close enough to do for anything you would ever deal with. It matters to the theorists. All right, now this number up front. The number up front is dependent upon the unit systems. Because I know that's in kilograms in SI, that's in meters, that's in newtons. I need something in order to get rid of those kilograms and meters and get to newtons. So that number up front is known as the gravitational constant. Some textbooks, and I don't know many today that are still saying this, but in case you run across it, I'll put this in parentheses, the universal gravitational constant. Some textbooks used to call it that, which was rather arrogant of us to say that it is true for the entire universe. All we can do is say it seems to be true right now where we are. But we don't know if it's universal. With the universe expanding, that seems to contradict certain theories. And so one of the speculations was perhaps that constant is not indeed universal. And then they came up with the current trend is to look at what's called dark matter or dark energy.
And this whole equation is labeled as you're solving for the force due to gravity.
Yes.
Okay.
This is the generalized equation.
Okay.
We get, that should be equal to little g. But generally mg is easier if you're at the surface of the planet. Let's see what we get rid of here.
So how is that different from the potential energy one?
The potential energy's got a negative in front, m1, m2, and then just a plain old r on the bottom instead of r squared.
Are they related at all?
Yes, they are. With calculus, you can derive this from that.
I was just curious.
Yeah. Generally, if you see the negative sign in a potential energy formula, that means it's based upon a force that causes attraction. The over R, you think back to energies related to work. Work is force times the distance. If I multiply this times the distance, I get rid of one of my distances down here. That's a very crude pseudo derivation. If you've had calculus and you'd like to see the derivation afterwards, I'd be glad to show it to you. So, let's do a little plug and chug. Helpful if people have calculators. So, the value of big G. Oh, and when I get picky, when you say what is the force, and you say gravity, and I go, what's the name of the force? There are three things that students tend to call gravity. There's the force due to gravity, or weight. There is acceleration due to gravity, little g. And then there's the gravitational constant, which some students will just label all as the same name. And that's why I get picky about it, because they are not the same thing. They are related, but they are not the same thing. So a big G in SI system is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. It is a constant, as far as we know. All right, so the gravitational pull between me and Isabella, I'm gonna make up your mass. I do not know what it is, nor is it really particularly important. My mass is about 100 kilograms. I'm just gonna say 50. I don't know whether that, what would that be? Yeah, probably someone way underweight. So the gravitational force between us, I got 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times my mass, 100 kilograms, times our make-believe person's mass, or the make-believe mass of Isabella, and then the distance between us, 3 meters. That's not good here. Over 3 meters squared. So this is the force, the magnitude of the force due to gravity. And if someone would be kind enough. Now, we're going to do a couple of problems which require a calculator. If you do not have your calculator, please make sure you know how to do it at some point.
3.705 e to the negative 8.
Negative 8
Yes.
units.
Newton.
Yep, that's a force. Just to put that in some perspective. The gravitational force acting on me from the Earth, oh, sorry, Jennifer?
Why did you divide by 3 squared?
Divide by 3 squared?
Yeah.
Because the R squared. We were estimating there's 3 meters between us.
Okay.
Because R is distance.
Because
R is distance.
yes. All right, so the gravitational force on me from Earth, so on George from Earth, is approximately 1,000 newtons. The gravitational force on me from Isabella is 0.0367307.5. Which is why when we were doing force diagrams, we tended to ignore it. You need incredibly specialized equipment in order to be able to measure things like that.
Why was yours 1,000?
That's my weight.
Oh, okay. And
Ish.
newtons, yeah.
My mass is somewhere around 100 kilograms. That times 9.8 puts me at 980, roughly 1,000. As soon as the pandemic struck, I was hanging out about 215 for a long time, and then I shot to 230, 230 something. And then I ended up dropping down to 194.
After you got COVID.
No,
Oh.
not before. I just stressed. I went stress eating to stress not eating.
Oh, there you go.
And now I'm back up to 220. Anyway, a fun fact.
You're pretty tall though, that's like a good average.
Alright, so let's figure out what little g is. I know that I should be able to figure out the gravitational force using our weight formula if I know what little g is. And I pretty much only know little g if I'm near the surface of the planet. But I also have that formula over there. So what I'm getting towards is, if I'm standing on the Earth. And I know that my weight is mg, but it also could be, so this is mass of George, also equal to that formula over there. G mass of George, mass of Earth over r squared. They should be equal to each other, whichever formula I use. Well, mass of George is on both of them, so my mass is actually irrelevant, which we've dealt with up till now. Gravitational acceleration is not mass dependent. So I got big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by R. What R do we use? If I'm standing on the Earth,
0? No.
that
I mean,
would make
there's,
this incredibly huge.
but there's no distance between you and the Earth.
So what is R? It is a distance, but distance between what?
Between you and the center of the Earth?
It's the center to center distance.
Center to center.
Yeah. So even the center from the ground to me is negligible compared to that of the Earth. But it would be, basically, R is that distance, wherever my center of mass is. So it's roughly 6.38 times 10 to the 6th meters squared. And if people would be kind enough to calculate that.
.799 newtons? No. Newton meter squared kilograms meter squared. Newton kilograms? No, I'm canceling that wrong. There's 2 meters on top and 2 meters on the bottom.
Right,
So
those go away.
Those go away. There's 3 kilograms on top and no kilograms on the bottom. Right?
That's a Newton meter squared per kilogram squared
Uh-huh.
times a kilogram
Yep.
divided by meter squared.
So the meters go away. It's not Newton kilograms.
Pardon?
It's not Newton kilograms.
They're not, if you say it that way, you left a word off.
Newton's not kilograms cubed.
No.
What are we not seeing? Newton divided by kilogram?
Yes, Newton per kilogram.
Okay,
That cancels out with one of those, and I'm left with a Newton per kilogram.
per kilogram.
Otherwise known as I thought you were saying something there, Isabel. What did we find? What'd you say?
Wait.
No, not the weight.
Little g.
Little g. What is little g?
I don't want to say gravitational pull
Because it's not.
because it's not, and he just gave us that speech on that.
What is little g? Or if you think about it in labs, what value do we use for little g?
9.798.
In the units?
Meters per second. Square.
There we go. Yeah. It's acceleration.
Wow.
Acceleration due to gravity.
Due to gravity.
Newtons per kilogram is legitimate. Meters per second squared is the more traditional way of writing it. Now, this is a crude approximation. The fact that the Earth is not actually a sphere. It is not actually a uniform density, but close enough. You see that we get we get the Winston-Salem value, which is just coincidence. But I would expect it to be somewhere around 9.8. Again, if you do not have your calculator with you, please make sure that you can work through using your calculator to get this answer. Yes? Juliana?
I can't. I don't know how to put it in my calculator. I'm not getting that answer, and I probably won't get that. I just have trouble with that. Maybe if I did profile it.
All right, so you got,
Does Newton kilograms turn into meter per
that
second squared?
square doesn't go there.
Because he had n over kg, right?
Wait a minute.
3.7
Yeah,
times.
no, we're not
Yep.
getting what she got. It's not, because she got 3.075. We got 3.
Oh. Should that be 7.0 instead of 0.7?
I can put it back in. Let's see.
Yeah, I think you're right.
Unless you type something in strangely, but
Oh,
Look like-
3.07. Oh, 3.70.
7.0.
Okay.
Okay.
Probably just a little dyslexic. That's probably what it is.
7.0. Okay. Thank you for pointing that out.
But did you guys get the second one?
Oh, we've been working on that one.
Oh, okay.
On it
I got
right
that
now.
one.
You got that one for the second one?
I got 9.799.
Yeah, see.
9.799.
Yeah, I put 7.
I see it rounds off to 9.
Isn't it like 9.7990? Yeah,
Oh.
990.
All right, questions?
So Newton kilogram converts to meter per second squared.
Newton per kilogram, yes.
Newton per kilogram.
Because a Newton, by definition, is a kilogram meter per second squared, and the kilograms would cancel.
Okay.
So let's figure out how fast that satellite's been traveling. Getting back to that problem. Leave that. There we go. So let's figure out the speed. That's right, threw it on the floor. So plugging in, we have a formula now for the gravitational force. That'd be big G times mass of the satellite times mass of Earth over the orbital radius squared. And so R is this distance from here to here. That would be R. That's going to be equal to mass of the satellite times its speed squared over R. So if we get rid, so multiply both sides by R, one of those goes away. Mass of the satellite goes away. And I'm left with the speed squared is equal to big G, mass of Earth over R. We need to fill in some numbers here. Mass of the Earth, big G, we got those. How far away is it? Why don't we make this distance here why don't we say that's the equivalent to the Earth's radius? In other words, the orbital radius, that big R there, is twice the Earth's radius. So V is the square root of 6.67 times 10 to the negative 11 times mass of the Earth, 5.98 times 10 to the 24th, divided by, so it's 6.38, 12.76 times 10 to the 6th. No, not squared.
The 12.76 times 10 to the 6th, that's 6.38
Times
times 2. Okay.
I'm confused as to where, the 5.98 times 10 to the 24, where's that coming from?
That's the mass of the Earth. I'm just presenting it to you. It's not something we